Thank you.
Thank you. Can you hear me? Good? Okay. I want to thank you guys for being here. It's an honor for me to be here at your 100th anniversary. And it's really nice. I'm enjoying your weather. It was 108 degrees in my house in Houston when I left last Wednesday. So to be here in a jacket is wonderful. I'm going to talk about this year's observing program, the telescope program, Observing Planetary Nebula, and try to make you aware of what these things are, what they're doing, why they're there, and a little bit about how the professionals have learned what we know about these objects. Planetary nebula are a very exclusive type of deep sky object, which a lot of people don't realize how rare these objects are. But stars with solar masses of 1 up to about 8 are the only stars that go through a planetary nebula stage. Stars that are more massive than 8 solar masses blow up in a supernova event. Stars that are smaller than our sun, density-wise, never get hot enough to form planetary nebula. So these are fairly rare events. There are some 200 billion stars in our Milky Way galaxy, and there's only about 3,500 planetary nebula that we know of so far. And of those 3,500, they're only visible for 10,000 to about 30,000 years. So they're very rare events. And someone figured out if the average lifestyle or lifespan of a person is 75 years, if you put that in planetary nebula stage, that would be about 30 minutes in that 75-year lifespan. So these are unusual objects that we're privileged to get to see. And we don't know the distance to most of them because what we call a central star is not really a star. Stars that spend most of their lifetime on the main sequence are fusing hydrogen into helium, helium into carbon, nitrogen, oxygen, so on and so forth. These stars are not fusing anything. They're gravitationally collapsing. And that gravitational collapse makes them get very, very hot. It's like if you rub your two hands together, friction creates heat. That gravitational collapse creates heat. But we don't know how far along in that collapse they are, so we don't know what the absolute magnitude of those so-called stars are, and therefore we don't know the distance. So all distances to planetaries are very relative. So well, this is not. Okay. The thing I like about planetaries is there are no two of them alike. We look at galaxies, and it's nice to see something 100 million light years away, but galaxies, a lot of times, they're just faint and fuzzy with maybe a brighter center. No two planetary nebula are alike. They're all different, and that makes them interesting objects. They're all shining by ionized light. They've lost electrons from the atomic structure, and that makes them glow. And that's the only reason that we're able to see them, because these are emitting a specific form of light that we're able to see. And that also makes them interesting, but they come in all shapes and forms and sizes. Some are round, some are elliptical shapes, some are elongated, but all of them are interesting. There's 5 different types of nebula. Planetary nebula are the ones that we're more concerned with, but there are emission nebula, supernova, which is the end results of very massive stars that are larger than 8 solar masses. Reflection nebula, which are gas and dust that doesn't get hot enough to radiate or to be ionized, so they shine by reflected light. And then there are dark nebula, which are not reflective or anything. They're just blotting out the background light. But we're more concerned with planetary and nebula. This is the end stage of stars that are in the process of dying. The next slide that I've got is a Hertzsprung-Russell diagram. And unfortunately, I have to get through this. I can make a whole talk on stellar evolution, but in order to understand what planetary nebula are, you need to understand how stars are formed, how they live, and in particular, how they die. Stars form out initially began as large clouds of gas and dust that condense, and that condensation eventually forms a star. They go through a protostellar phase, and they end up on what we call the main sequence, this line here, and specifically the zero-age main sequence, which you typically see referred to as the ZAMS, Z-A-M-S. Astronomers like abbreviating as much as NASA likes abbreviating. But where that star ends up on the main sequence is the most important aspect of that star's future. Stars that are very massive are O-type stars. They start out up here. And this scale, by the way, the x-axis to the left is hotter, to the right is cooler. On the y-axis, we have larger massive stars and smaller stars. So that's kind of the way it works. But your very massive stars are very hot, and they're very large, they're very massive. O-type stars have a life expectancy of about 5 million to 10 million years. That's million, not billion. They burn through their reserves at a ferocious rate. They have a mass of about 10 to 50 times the size of our sun, and there's very few of them. But when their lifespan is up, they go through the supernova phase, and they literally blow up. B-type stars have a life expectancy of about 30 to 40 million years. A-type stars have a life expectancy of about 350 million years. F-type stars are about 3 to 4 billion years. And G-type stars, like our sun, will last for an expected 10 billion years or so. So when we look at a star cluster, if we see O-type stars there, we know it's a very young cluster. If there are no O stars, but there are, say, F-type stars that are the oldest stars in that cluster, then we know that cluster is probably 3 billion years old or so. So we can tell by the oldest type of stars how old a cluster is. So the stars are quietly fusing hydrogen into helium all along here, and as they get further along in their evolutionary scale, the balance gets thrown off. Normally, the internal outward combustion is matched by the gravitational collapse. So the star is operating in a state of equilibrium. But as things go along, as time period goes along, the interior of the star gets hotter. It causes the star to swell, and the star enters what we call the red giant phase, or the RGB phase, and that lasts for maybe 2 billion years or so for a G-type star like our sun. And as it gets bigger, it starts expelling the outer atmosphere. It starts gently drifting away, anywhere from 6 to, say, 20 miles per second, which sounds fast, but really it's very slow as far as a planetary nebula stage goes. So the star is getting bigger. The outward portions are getting cooler because the given amount of heat is being spread out over a large area, so it becomes what we call a red giant. And if the star is big enough, it begins to fuse the helium core which is developed during the hydrogen fusion of the star when it was on the main sequence, that it starts fusing the helium core in an event we call the helium flash. That's stars that only get an interior temperature of 100 million degrees or so. Our sun will probably go through a helium flash mode, but that's about as far as they think our sun will go. Our sun, having a solar mass of 1, is on the lower side of becoming a planetary nebula, and it is thought that our sun will probably be a round spherical planetary nebula. But anyway, stars that are large enough to go through the helium flash, they start burning or fusing helium into carbon. So you have a degenerate carbon core. Like on the red giant phase, we had a degenerate helium core. And when I say degenerate, it's a very massive, very compact collection of material. The typical atom is composed of protons, neutrons, and the electrons are in orbit around it, kind of like the solar system, if you will. And if you thought of the sun as the nucleus and the planets as the electrons, well, that would be a typical atom. So most atoms are empty space. A state of degeneracy, all the electrons are fused into the bottom layers, the bottom channels that the electrons can be in. So if our solar system became degenerate, Mercury and Venus would share the orbit of Mercury. All of the rest of the planets out to Neptune would be in the orbit of Venus, and that's it. So a teaspoonful of that material weighs several tons. So degeneracy is a very unusual state that only happens in stars, and when we have this helium flash, all of a sudden the degenerate helium material becomes gaseous helium. And it goes along what we call the horizontal branch. It's forming carbon. And if it's massive enough, the carbon starts fusing, forms nitrogen, forms oxygen, forms neon, magnesium, silicon, so on and forth up to nickel and iron. But it goes through a second enlargement, which we call the asymptotic giant branch stage, or the AGB. And from here, stars go through a protoplanetary phase, which lasts about 2,000 years, and they become true planetary nebula. And they'll get hotter and hotter, but they don't get any brighter. So it's kind of a horizontal movement on the HR diagram. And they end up in a cooling phase, and they ultimately end up as a white dwarf, and eventually will end up as a black dwarf and disappear from the system. So what we're going to be concerned with is more this area up in here. So I'm going to try to abbreviate some of this because this took longer than I thought it would, but that's stellar evolution for you. But anyway, there's two ways that a star can go. You can have a very massive star, which ends up as a supernova explosion, and from that supernova we end up with a neutron star, which is about the size of 20, 30 miles in diameter, something of that nature, that is totally made out of degenerate material, very heavy, very condensed material. Or if it's large enough, it ends up as a black hole. There's something called a Chandrasekhar limit, that if the star, after it throws off all of its material in the AGB or the RGB phase, that if it gets down to 1.4 solar masses, it can support a dwarf, a white dwarf star. If it's between 1.4 and about 3 solar magnitudes or solar densities, it becomes a neutron star. If it can't get below 3 solar masses, then it becomes a black hole. It's pretty much the way that works. Now, stars like our sun will go through a red giant stage, planetary and nebula stage, and end up as a white dwarf. So that's kind of an abbreviation of stellar evolution and how things work. As far as classifications go, spherical planetaries, which is what they think our sun will end up looking like, because right now we don't know that our sun has a companion star, and most stars that are single stars end up as a spherical planetary. And it's only thought about 10% or so that end up looking like this. Irregular planetary nebula, which have no defined shape, but they're thinking now that that might be the product of a triple star system or a star with a large planetary nebula system that would cause a irregular shaped planetary nebula, kind of like NGC 6572. Elliptical planetaries, like NGC 6826, are about 20 to 30% of those are thought to be elliptical shaped planetaries. And 6826, or the blinking planetary, is an excellent planetary for you guys to look at. And I'll talk about that in just a second. The largest area and the largest type of planetary nebula are what we call some people refer to them as butterfly-shaped planetary, bipolar planetary, with a tight waist, and about 43% of all planetary nebula are thought to be of this shape, like the bug nebula. So the large majority are like this, and they're thought to be the product of a binary system, two stars that are gravitationally bound together, and that causes the bipolar shape. Part of the shapes of the planetaries that we look at is a viewing perspective. If we look at a bipolar planetary from the side, we see something like the Bug Nebula. If we see it from an angle, we see it similar to NGC 2346. If we see it from a pole-on orientation, we see it as the Ring Nebula, which all of us hopefully are familiar with. The Eskimo, when we look at the Eskimo planetary, these are the bubbles. This is the fast wind that's blowing that bubble out. The slow wind is this equatorial disk, which was expelled from the AGB or the red giant branch stage, that slow 6 to 25 mile an hour wind that I was talking about. That is the fur of the Eskimo. Again, this is perspective. So if we look at the Ring Nebula, the part that we see is this area in here. This outer halo is a low ionization area that is basically shining in the light of nitrogen with one electron missing, nitrogen 2. And I brought a visual. This is from a veterinarian's place. They call this thing a collar of shame for dogs. Our vet calls it an Elizabethan collar, and I'm sure Elizabeth I of England is spinning in her tomb right about now at Westminster Abbey for me telling you about this. But the Ring Nebula, this is what it looks like. It's a bipolar planetary nebula. These jets that are coming out of the star that are wobbling are creating this halo, and that halo is what you see out here. But we don't see it from this perspective. If you guys are the people on Earth with a telescope, you're seeing it like that. That's what you're seeing. So when you see that halo, you're seeing what we call the torus. This is the initial ejection from the star. When it starts losing material, it's going to lose material along the equatorial region, like the rings of Saturn. And that's what that is. And that's what you're seeing. This halo, this outer lobe here is the outer lobe up there. Now down below is this is the Earth view, and then if we shifted it from the side, this is what we would see if it were like so, right here. This is what we call the torus. This is the initial ejection of the material in the AGB or in the RGB phase of the red giant star. So essentially, that's what the ring nebula is. And a lot of people, I mean, that's fairly recent. They used to think the ring nebula was a big sphere, and this was the edge of the sphere, which from our perspective would be brighter. We now know that that's not true. It's a bipolar planetary, and one of the best views that I've seen, you can see it there. This is the forward lobe. This is the backward lobe. And it's pinched in the middle, which we don't see because of these outer lobes. So that's a little bit about the ring nebula. All right, as far as what makes these planetary nebula tick, the internal detail within them, you have the central star. That central star can be up to typically 200,000 degrees external temperature. Point of reference, our sun is 5,200 degrees external temperature. So a 200,000 degree temperature star is very hot, and it's going to ionize. It's going to strip electrons off of the atoms that are external to the core, the central region of that star. It's going to create a vacancy. But that vacancy, as that star gets separated from the surrounding material, that star starts blowing material out at a very high rate of speed that we call the fast wind. That fast wind goes anywhere from 600 to about 2,500 miles per second. It's extremely energetic. And that fast wind is this region in here, and it creates what we call a bubble. And you'll see this on some of the planetaries that I'll show you in a minute. But this bubble, this fast wind bubble, is pushing against the next layer out, which is called the shell or the envelope. And this is ionized, but to a lesser degree. And this shell, this shell area is actually larger than this. I mean, it's normally the biggest part of the planetary. But as that shell expands outward because of the fast wind slamming into it, it reacts with the interstellar medium and the halo, the material that was previously expelled from the red giant stage and the asymptotic giant stage. So you've got a shock front, you've got a shock front, and you've got a shock front, where these different regions of the nebula are snowplowing into regions external to it that are moving slower. And all of that causes the nebula to glow, and that glow, that ionization, is what we see in our telescopes. And when you put an O3 filter, an Oxy 3 filter on there, or a UHC filter, you're allowing that particular wavelength of light to come through, which is why those filters work. They block out everything except the light that we see for these planetaries. Now, the blinking planetary is a good example of what I just showed you. Right here is your bubble, and you can see the shock front. The fast wind and that bubble is blowing into the slower expanding level of activity. You can see here, the halo here, this is the asymptotic giant branch halo, and external to that is the red giant branch halo. Red giant branch halo went first, then the AGB halo, and now the fast wind is impacting both of them and causing this entire structure to glow. And that glow, again, is what you see in your telescopes. These two features here are called ONSE, or flyers, and I'll talk about it in a minute, but those are features that they don't really know why they're there or how they got to be there. There's a good recent theory that's probably pretty good, but we're not sure really why these features are there. ONSE is a Latin word for handles on a cup. FLIRE stands for fast low ionization emission regions. They used to be called ONSE. Now you typically see them in the literature referred to as flyers, more so than ONSE. But this is a very bright object. We looked at it last night in various telescopes. You can see these ONSE, by the way, as protrusions on the eastern and western side of the nebula. If you crank it up to about 500 power. They don't respond to a filter, but they're little blivets that's sticking out, and you can actually see that. And you can see the bubble in here if you power it up to 500 or 600 power. We call it the blinking planetary because if you stare at the central star, that star pops out, but the nebula tends to fade. But then if you use averted vision and you look at the nebula, then the star fades and the nebula pops out. So you can go back and forth, bright, dim, bright, dim. And that's why they call it the blinking planetary. And most people, they look at it, okay, it blinked, and they go on to the next thing. If you stop and take a moment, you can see that detail. You can see the inner shell or envelope and the outer shell, the RGB shell or envelope, if you look. Now, exterior to this is the halo. This little area here is here. This halo, this is the RGB, the red giant branch stage and asymptotic branch stage material that has not been impacted by any fast wind or anything. This is shining in nitrogen-2 light. It's shining in helium or hydrogen-2 molecules. Some of the area out here on the outside is what we call recombination, where it no longer becomes ionized. The electrons literally come back and form molecules. So this halo is much, much larger than the ionization structure that we see here. Oh, okay. My computer crashed this morning, so I'm kind of, I don't know what I've got on this program or not. But anyway, this just shows you what I just talked about. This is the core, the fast wind bubble, the super wind. They sometimes call the level of expansion exterior to the fast wind. And AGB shock and the RGB shock zones, where the faster material is slamming into the slower material. The blinking planetary is seen in different light, and this is how the professionals can analyze a lot of this material. When we look at it in the light of singly ionized nitrogen, we can see the ONSE. We can see the shock fronts much better. That light is shining at 6583 angstroms. Hydrogen alpha light is 6563 angstroms, so it's very similar. Sulfur 2 is good for density, for determining how this is a denser region, this is a denser region. So sulfur 2 is good for determining the density or enhanced regions. And then, of course, oxygen 3 is very violent, very 5007, 4959 angstroms, very active, energetic regions in oxy 3. So by looking at it in different light, we can tell a lot of the internal structure of these planetary nebulae. This is the Egg Nebula. I mentioned a minute ago about protoplanetary nebula. The phase between the asymptotic giant branch stage expulsion of their outer envelope and before it becomes a true planetary nebula, we call a protoplanetary or pre-planetary nebula stage. And basically, this is an area that the central star is not hot enough to ionize the surrounding material. So it's left the asymptotic AGB stage, but it hasn't quite got hot enough to ionize this material here. The central star is only 7,000 degrees Kelvin. And it is strong in hydrogen cyanide, which is a progenitor of carbon stars, and a lot of these are building molecular carbon, basically. And the carbon that we have here on Earth started out in the core of a protoplanetary nebula. But this is all basically the same features that you see in a planetary, and there is some confusion because some people, some astronomers consider protoplanetaries as planetaries. These are also confused sometimes with nova, sometimes with symbiotic stars, sometimes with proto-stars, because stars that haven't formed yet look and spectroscopically are very similar to a protoplanetary nebula. So, but these are interesting to look at. Back in 2003, on an exceptionally good night, with my 36-inch telescope, I saw it just like that. The two headlights, the arcs, and everything. So if you get a good night and you have aperture and you don't mind looking at something at 700 or 800 power, you can do it. You can see that. Yeah, that's available. You don't need infrared eyes to see it. All right, bipolar planetaries. These are, I kind of covered this on the internal structure, so I'm going to move on. But the structure is a hot bubble, a nebula rim, envelope and shell, a halo, and the concentric rings or arcs. These concentric rings were just discovered back around 1990. So that's a fairly new discovery. This is the bug, NGC 6302. This is a very, very interesting object. It's too bad it's very low in your sky here. It's in southern Scorpius. Steve saw it last night. So it is doable. It has a high surface brightness, but it's one of the highest excitation planetary nebula that we know of. And it was only recently categorized as a planetary nebula because it's so energetic they didn't know what kind of a classification to make for it. It's also one of the most massive planetaries that we know of. There's over 750 papers that have been written about this object. And it's so energetic that it's ionizing iron inside. This is in different light. But the interesting thing about it is you don't see a central star here, nor do you see it here. And actually, nor do you see it anywhere. The Hubble Space Telescope has not been able to find the central star. In 1990, they found a star that was very close to the center. But unfortunately, in 2020, they found that the proper motion of that supposedly central star had 125 miles per second, which is much faster than the proper motion of the planetary. The two could not possibly be related. So what they thought was a central star is a foreground star that has nothing to do with the planetary. It is very dense, dusty torus. It's very bright inside, and they've not been able to find it yet. Maybe the James Webb Telescope can pierce through that dust, but estimates of this central star have gone up to 430,000 degrees Kelvin. That's over 8 times hotter than our sun. That's incredible. I mean, that's about the hottest star that we know of in our galaxy. and it's right in the middle of this object. They estimate the brightness of that star is about 21st magnitude. The Taurus is very young, about the Taurus being this feature here. The Taurus is the initial explanation of material from the star, and that acts as a constricting belt so that subsequent further ejections go out the polar regions. So this star is rotating in this direction, and after this belt constricts material, from there on, material goes out the polar regions. And that's what makes the bipolar nature of these objects. These lobes extend 4.9 light years, almost 5 light years, and it's a huge, massive object that they're still trying to figure out. Well, okay, this is a close-up of the central region. This is the iron that's lost. Fe2 means it's lost 1 electron at a temperature of about 11,000 degrees Kelvin, and you can see the blowout in the northwest and the southeast regions. Of interest are these clumps here. And I'll talk about these in a second, but if you notice, the front is on the inside towards the star. They used to think that these onsae, these lobes that were pushed out from the star, that they were bullets that were ejected from the star. If they were ejected from the star, the open end would be towards the star, but it's not. The shock front is towards the star. So something is happening here that they've just recently have a good theory of what is causing that. Material is being thrown out and it's slamming into something. Something is happening there, and they think they have a good idea of what it is. But anyway, this is the center of this object, and I'm running low on time, so I'll go on, but there's a lot of activity here. Now, unfortunately, and I have looked at all powers up to my 36-inch telescope. I've looked at it with an 82-inch telescope at McDonnell Observatory. I can't see this. You cannot see this pinched in waist for whatever reason. It looks like that in a telescope, in an amateur telescope. This is the waist here. So you cannot get that butterfly look. Sun Kwok, who's an expert on planetary and nebula, called them cosmic butterflies. That does not look like a butterfly, but it does look like something else. It looks like a bug splat on a windshield of a car, and that's how it got its name, the bug nebula. So anyway, that's what it looks like as opposed to what the professionals say. All right, a little bit about these flyers or these onsae. As I said a minute ago, they really don't have a good idea of what these objects are, but they think they know. Sun Kwok from Calgary has done a lot of work on these. An astronomer out of Seattle, Washington, Bruce Balick, has done a lot of work on these. And they've come to a good, what they think is a good understanding. These objects are best seen in nitrogen, oxygen-1, and silicon-2 light. All of those are states of different ionization, but they're low states of ionization. 6583, that's much lower ionization rate than, say, oxygen at 5007. So they're younger than the slow expanding halo, but they're older than some of the features. And essentially, without going through all of this, what they think is happening is as this star collapses and it gets smaller and smaller, it rotates at a faster rate of speed, kind of like an ice skater. When she comes in, she turns faster. Same thing with the star. And after it throws out that equatorial region, subsequent ejections go through the poles. The initial ejection from the poles is a jet, and at the head of that jet is a lobe, is a knob, is one of these things. And as that ejection goes further away from the center and it encounters less and less dense material, it becomes thicker. And being in the initial ejection, it's the thickest of all of the knobs, or all of the ejections. And it lasts only about 1,000 years, but they think that what happens is it runs in to the magnetic field of the star. And that is what causes it to glow, and that's why the tails of these objects is facing outward instead of facing inward towards the star. Like if it was an ejection, you'd expect the tail to be facing inward with the most shock front being on the outside, but it's just the reverse. The shock front is on the inside. So what is happening is it's running into that magnetic field, and that is what is causing these onset or these flyers to glow. Well, that's the theory anyway. And since these, they've also figured that the rate that these are moving at is no faster than 25 miles per second, which is very slow. The wind is moving past them, so they're not moving fast enough to ionize anything, not even to ionize nitrogen. And since there's no oxygen present, there's nothing from the central star. So that is a pretty good theory. They think it's from the magnetic field. And this is just a quick diagram. This is the torus, and this is the toroidal magnetic field that these onset are reacting with. So the Cat's Eye Nebula, NGC 6543. This is a beautiful object, high surface brightness object, easy to observe, easy to see. It has these outer rings, these outer arcs, which was discovered in the early 1990s. And these are the ejections from the red giant branch stage and the AGB stage. And they come in discrete puffs of about 1,500 years apart. Each one of those rings contains several Earth masses of material. They're moving outward at a very slow rate, maybe 6 miles per second, and they have yet to feel any of the fast stellar winds coming out from the central star. And it's virtually impossible to see this in amateur telescopes. It's just too faint. And they have to image most of this from out in space, from the spaceborne telescopes anyway. But the central star is thought to be a binary system because it is a bipolar system, and you can see multiple rings inside. And the reason for those multiple rings and how they're shifted is because of precession. Our Earth is precessing. When the pharaohs were in power 4,000 years ago, Deneb was a North Star. So our Earth is shifting, kind of like a spinning top. Well, this star is doing the same thing, and as it sends out these beams, it cuts different paths through the planetary. And you can see these different concentric rings. They call it the cat's eye because the concentric rings cross in the middle, and that reminded somebody of a cat's eye right there, and that's how it got its name, the Cat's Eye Nebula. And here again, when a warped disk spins, it wobbles, and that wobbling of the star and that jet is creating those rings, that spirograph type structure of these rings. So that's a little bit about what's causing the internal structure, and that's fairly new information, by the way. that has been gleaned in the last 20 years or so. And this is what they think overall the structure is. You've got two different lobes that are constricted and formed by those spiraling jets, the precessional jets within the nebula. And here you've got the nitrogen 2 cap on the outside, and different features that you can see. There's a lot of material there. Another interesting feature of this is this knot right here, IC 4677. They really don't know what that is because, as I've explained, these ejections go out through the polar regions. So that knot should be either up here or up here, not along the minor axis, but there it is on the minor axis of this object, and there's not one on the other side. So they're really not sure how it got there, but they think it's some kind of a hiccup that happened during the red giant branch stage. That something happened and it was expelled on that side only, and it stayed there. The halo, the outer halo, is moving at only 2.8 miles per second, yet that halo is moving past that knot at that slow rate of speed. They have no answer for why that is. But you can see that in a telescope. You can see this feature here. It's much further away from here than you would think, but you can see it on a good dark night with a, say, 20-inch telescope, which I've seen in mine, fairly easily if you know where to look. It's on the western side, of the planetary. All right, NGC 6210, it also has a flyer here, and there's another one down here, but unfortunately the Hubble Space Telescope image cut it off. But this is one of the highest surface brightness planetaries in the sky. It's in Hercules, and it's well placed for viewing here at the Texas Star Party. It's 38 degrees above the galactic plane, so it doesn't have a lot of interference with viewing it. And it's a kind of a jumbled up mess. I mean, there's really no organization to it. It's thought to be a low surface brightness or low density star because its helium, oxygen, and nitrogen abundances are about that equal to our sun, if not lower, and the carbon content is much lower. So it has not gone through a helium stage, helium flash stage, and it is not anywhere near as massive as our sun. So they're kind of at a loss as to why such a low density star can create such a highly luminous nebula, but nevertheless it has. And they call it the turtle. And it's composed of two regions based on the inner region and an outer region, and you can see here the flyers fairly well. One of the nicest planetaries for amateurs to look at that you can see internal detail is the Saturn Nebula. You can see the ONSE or the flyers very easily in moderate-sized telescopes. You can see both what we call the bubble or the inner halo and the outer halo. It's an optically thin nebula, so you can see this detail fairly easily in small amateur telescopes. And it also shows color. It looks like it has a blue-green appearance to it, so you can see the oxygen 3 emission. This is a wire mesh model of it, and you can see the precession. This is the torus ejection over different stages, here, here, and here. And you can see how they're shifted. That's precession. And you can see why the bipolarity would shift from here to here to here. And again, you got the outer shell, the main shell, and the outer halo. All of this detail in moderate-sized telescope, you can see it, and it looks very similar to the picture on the left. And again, this shows the ejections of the ONSE, or the flyers, and the ejection of material from the central star. And again, anytime you see bipolarity, you're probably looking at a double star in the center, one of which is ionizing the halo, probably a white dwarf, and its companion is probably a main sequence star that is yet to go through that white dwarf evolutionary stage. The current what now?
A recurrent nebula with the main sequence star and a white dwarf.
You would only see the one star, if that's the question.
What happens is the main sequence star starts giving material to the white dwarf, which then accumulates it and then has explosions.
Yes. And that probably is happening, but they don't know. The question is, does the main sequence star, is it losing material to the dwarf star? And that is a very distinct possibility. They call that a symbiotic system. And that does happen in these objects. And the fact that the bipolarity, each star is operating against the other star. The main star causes the dwarf star to spin up, and that rapid spin up is where you get the jets coming out. So the two of them work hand in hand together. Yes, very much so. The NGC 6445 is an interesting planetary in that you can see, this is the torus, and in large amateur telescopes at high magnification you can see that. That's a molecular ring of material, and it is fairly bright. And over here is a artificial image where it shows the nitrogen 2 ionization structure, which is the lobes, and also the H2 region. This is molecular in nature, and they think that maybe there's an extra halo or extra lobe that is there, that is showing up in the hydrogen 2 molecular structure. When you look at this with a filter, you can see all of this, and I was able to see some of this halo here, maybe out to about here. So you can see a little bit of the external halo, and again, all of this is from the red giant asymptotic giant branch stage. So this is yet to feel the effects of the fast wind. It's a very low ionization structure that you see externally. And here, the red 8 micron structure, this is dust. This is carbon dust that comes from polycyclic aromatic hydrocarbons, or PAHs, P-A-H-S, you typically call it. All of the carbon in us, this building on Earth, and everything came from these things. And that came from Planetary Nebula. As the halo expands, it gets cool enough, it starts recombination, it forms carbon soot, carbon dust. This is why carbon stars appear red, because you're looking through all that soot, you're looking through all that carbon, and only the red comes out. So these planetaries, and this one in particular, has a tremendous amount of carbon structure that's forming. And again, that is observed in satellites that are observing at 8 microns or so. All right, the Cheeseburger Nebula that we looked at last night. In a telescope, I'll show you in a minute, but this is the torus right here and right here, and that's basically what we see. You don't see the halo emissions, and this is a This is a massive object, but it's only 1,500 years old. I mean, it's very, very young. Its progenitor, before it became a planetary, was a little bit larger than our sun, about 1.1 density. And right now it's down to about 0.56 solar masses. And it has a terminal wind velocity of 2,175 miles per second. So this is a very energetic material, and you can see it's blowing out the lobes. It's blowing out the material. It's very, it's a very energetic structure. It's blowing out lobes and knots. I don't know if you can see, but those are pictures of the individual knots that have been blown out of the center of this object. And these are similar to the onset, but they're a little bit different in that they travel along the inside of the lobes and end up in various places as opposed to the polar ejection. But there's a lot of them in this one, and there's a lot of them in the next one that I will show you as well. This is what it looks like in an amateur telescope. And I saw it in Houston through some of my observing buddies, Steve and Amelia Goldberg's 15-inch telescope, and we saw it last night in Eileen's 13-inch telescope. Those were with the dark lane down the center, if you remember. And you can see this in small aperture telescopes. These two lobes are these two lobes here. That's what you're seeing. You need to power it up. You need to get 300, 400, 500 power. But if you do that, you can see these individual lobes inside this object. And you see 7027. This is the most extensively studied planetary nebula of all of them. This thing is incredible. It is very young, 10,000 years from the AGB stage, and it's incredibly bright, and looks like we got some weather coming in. But it looks very, very similar to this. I mean, when you look at it in a telescope, you can see the lobes. You can see the pinched-in waist. This is the torus here. You can see that in the middle, it's kind of hourglass shaped. It's pinched in a little bit if you use sufficient power, and it's extremely energetic object. If you look at it molecularly, the torus, it's a figure 8 type structure, like so. And this is what you're looking at with the star in the center. You don't get that impression when you look at it, but nevertheless, you got a ring here, you got a ring here, and this is what you're looking at. And as for the composition, you got molecular hydrogen, you got your carbon, you got your singly ionized nitrogen, you got your shell, you got the central structure here, your ring or your torus. These are all standard features that are in Planetary Nebula. And a lot of this material has been gleaned in the last 20 years. I gave a talk on Planetary Nebula in 2003 at the Texas Star Party, and back then we didn't know any of this. So all of this is fairly new information that has come about in the last few years. The central star here was considered very elusive. It wasn't discovered until 1988, and is similar to the central star in the Bug Nebula that I was talking about earlier. These stars that are very hot are not radiating in visible light. They're radiating in ultraviolet light, UV light. And the Hubble Space Telescope can't see that. The James Webb Telescope is operating in the opposite direction, in the infrared. So I don't know if the James Webb is going to be able to find the Bug Planetary Nebula central star either. But nevertheless, they've imaged it. This is a HST image of it, and it's quite evident now. Before it went planetary, it had a mass of about 3 solar masses. And they figure it left the asymptotic giant branch stage maybe about time Stellafane was having your first star party. as recently as 100 years ago. So that's brand spanking new as far as things go in the universe. And a fairly new criteria is called the Intermediate Luminosity Optical Transients, or ILOT. They've started classifying these bipolar planetaries by ejection events and how the ejection events shape the planetary. In order to meet that classification, it has to be a linear velocity and distance structure, has to be bipolar, the lobe expansions have to be greater than 62 miles per second, and it has to be a total fast outlay of kinetic energy. NGC 7027 is probably the youngest ILOT planetary that we know of so far. And these are some of the ejection structures. Outflow number 1, this one in red, is they think that occurred only about 100 years ago, when Stellafane was having their first star party. So this event, this structure here, is only about 100 years old. So these are some of the ejection events that are taking place right now inside this planetary. And the last object I've got is NGC 6369. We did not look at it last night, but it's in Ophiuchus. And if you guys want to see a perfect donut, this is it. It's incredible, and it's high surface brightness, easy to see, easily seen, and also fairly easily found. But it's got an outer shell, an inner shell, central star, 67,000 kelvins, up to 106,000 in helium. And it's, as I say, it's fairly easily seen. That's what it looks like in an amateur telescope. And here again, this is what you're looking at. This is what you're looking at. But outside the main shell, this is your nitrogen and your molecular hydrogen and carbon emission on the outside, which you really don't see. But this is one, if we get a good view tonight, which is looking doubtful right now. But you guys that are doing the planetary list, be sure to look at 6369. If you haven't seen it, you'll be surprised. It's very, very easily seen. So I like to leave with a little something, and I recently discovered this, but it says, clearly the best time to be alive is when you start out wondering and end up knowing. There's only one generation in the whole history of mankind in that position, and that's us. We're very fortunate to be astronomers and to be interested in astronomy, because we're the first and only group in the history of the world that can answer that question, you know. And the other nice thing about astronomy is that they're making discoveries every day. Every time they point HST at something or James Webb Telescope at something, it's a new discovery. And we get to be part of that ride for free. So that's, I think, quite exciting, and I think most people find that exciting. So with that, I thank you guys. Thank you very much. And it did not take me an hour and a half to do this. Are there any questions? Yes.
Are you aware, have any of these been animated to sort of show the evolution over time?
Not that I know of. Not that I know of, but that's a good question. Yes, sir?
As an amateur, when we're looking for these objects, it's difficult for me to wrap my mind around how big the things should look through a telescope. Are there any references that you know of that will compare these type of objects to like some known size, like Jupiter or Mars or anything like that?
Well, yeah. The question is, when you're looking through an amateur telescope, is there any way to reconcile how large these things should appear in an amateur telescope? And the answer to that is, yeah, you can compare it to Mars. 20 arc seconds is a big Mars. 25 arc seconds is a big Mars. Many of these planetaries are 20 arc seconds or 25 arc seconds. One thing I have found out, however, if you're doing visual work, and whenever I did the TSP planetary nebula list, I went through 300 planetaries to try to come up with 40 that had unusual names. And a lot of these, they say they're 20 arc seconds or 25 arc seconds, but when you look at them, they're completely stellar because you can't see the envelope. You cannot see the shell. So if it's not an NGC planetary, if you're looking at Minkowski or something that has an unusual name, you probably have to look at it to see what you can see. But yeah, compare it to Jupiter, compare it to Saturn, and most of the planetaries that are nice visual objects are between, say, 10 and 30 arc seconds in diameter. So, okay. Yes? The most difficult planetary nebula that I have observed, that is the question. A planetary nebula that is in the galaxy M31. I like to look at that kind of stuff, and I've got a telescope that can do it. But yeah, that's probably my most difficult observation, and I think I saw it. It's yes, I did. No, I didn't. Yes, I did. No, I didn't. We have a rule at Texas Star Party. If you think you saw it 3 times, you probably did. Log it and go on to the next one. I thought I saw it 3 times. Yes. Well, yeah. The one in M22 is actually easy to find. There's one in Palomar 9, there's one in NGC 6441, there's one in M15. P's 1 in M15 will actually blink with a nebula filter. It's on the northeast side of M15, and if you can star hop over to it, and I've got a book that's being published by the AAS will take you right to that planetary nebula in M15. And once you get there, you can blink it with a filter. The one in M22 is marginal as far as blinking it. The other 2 are very difficult. It didn't? But you saw it? Yeah, you can see it. Try Peace 1, try 6441, try Palomar 9. I know of 3 people, and I'm one of them, that have seen all 4 of them. But they're doable if you and you can go to the professional publications, and it'll tell you how to find Pal 9 and 6441. So it's possible. Any more? All right. Well, thank you guys again.
Thank you. We'll see you back here for the evening keynote speaker and the raffles.
Do it.
And thank you for doing this year's Observing Olympics.
Thank you. Oh, yeah, I did want to announce, and I forgot to announce. You guys are known for building telescopes. I'm pleasantly surprised you're excellent observers as well. Last night, we handed out 27 observing pins for these planetary nebula that you guys did in basically one night. So I've been trying to find objects that are relatively easy for you. The gloves are off. Next year, we're going to do some open clusters, and I'm going to give you some Kronberger double clusters and things of that nature, but y'all can find them. You're good telescope builders, but you're good telescope users as well. So.
And anyone who did at least 10 planetary nebula last night, or 10 binocular objects, since it doesn't look like there'll be any observing tonight, please see me, and you will get awarded a pin.
Yep. you get one of these.
Enjoy your dinner.
Thanks again.